In today's lesson, we are going to be learning about the chemistry term called the mole. Please make sure that you watch this on either your phone or your computer so that way you can take notes on your iPad as you follow along. Before we begin this unit, I would like to take a quick minute to refresh on how we do sig figs. So how many sig figs are in each of the following? Please pause this video and try and do these on your own. Okay, now that you have tried this on your own, I'm going to go through and help you. So how many sig figs are in each of the following? Well, first thing we need to remember is that leading zeros never count. Any zeros that are before an integer are never significant, so those three do not count. Integers 1 through 9 are always significant, and then trailing zeros, which are zeros that come after an integer, can be significant if they're after a decimal point, which this 0 is. So this 0 is trailing, it's after a decimal point, therefore it is significant, so we have 3 sig figs. Again, we don't even have to look at integers since they are automatically significant. However, this 0, it is trailing, it's after a decimal, therefore this one is also significant, so we have 4 sig figs. These zeros are all trailing, however you will notice there is no decimal point. Therefore, there is 1 sig fig in this answer. And then in our 600 here, these are trailing zeros, and there is this decimal. Even though there's no numbers after the decimal is there for that reason. So therefore, this number does have 3 sig figs. In this case, how many sig figs should be in my final answer? Well, when we multiply anything, we need to just use our least number of sig figs. So here I have 3 sig figs. Here I have 4 sig figs, so in my final answer we should have 3 sig figs. Anytime you multiply or divide, you always follow whichever number had the least number of sig figs. That's how many sig figs you will use. In question number 6, we have 3 sig figs and we have 1 sig fig. Therefore our final answer should have 1 sig fig. Questions 7 and 8 are now dealing with addition and subtraction. When we work with these, we always round to our least accurate, or I should say least precise, measurement. Well, in this case, we're going to the hundredths, and here we're only going to the ones place. Ones is going to be a less precise measurement. So when we go through and solve for this, we are going to get an answer of 3.23. However, we can only be as precise as our least precise measurement. So in that case, we need to round this answer to being just 3. For question number 8 now, we have the numbers 57.9 and 43.85. So in this case, this is going to the tenths, but this one was to the hundredths. Therefore, 57.9 is going to be our less precise measurement. So when we go through and do this math, we get an answer equal to 14.05. But since our least precise measurement went to the tenths place, we need to round our answer to the tenths place. So we would not say 14.05. We would say 14 point, and a lot of times we round 5 up, so we'd say 14.1 would be our final answer there. And the reason that I wanted to take time to review this is because throughout this entire unit, you do need to follow your rules of significant figures. And actually, that holds true for the rest of any chemistry course you will take. Alright, so what is the mole in chemistry? Clearly we're not talking about the biological, the animal, the mole. A mole in chemistry represents a specific number of particles. So what I mean by that is, it's kind of like the number a dozen. If I told you I have a dozen eggs, well, how many eggs would you say I have? You would tell me 12. Well, what if I had a dozen tractors or a dozen ponies? No matter what, if I said I had a dozen of something, you're going to tell me that I have 12 of it. Seems kind of like a weird question, right? Well, let's continue on and see how this is similar to the mole. So, just like when I talk about a dozen being 12, a mole in chemistry represents a specific number of particles. That is, a mole in chemistry is just equal to a much larger number of 6.022 times 10 to the 23rd. This is also known as Avogadro's number. So, just how large is this number? Well, let's take a second to write it out. So here I have 6, and now there's going to be 23 numbers after it. So I have 6, 0, 2, 2, and now we're going to have 20 zeros remaining. So and as you can see, this is a very, very, very large number. And I'll talk more about and give you some examples of how large this number is in a couple slides. The point is, whenever you hear a mole of something, you need to be thinking of this many particles. Just like when I say a dozen, you think of the number 12. So let's play a familiar game. If I told you I had a mole of eggs, how many eggs would you say I have? Well, I would have 6.022 times 10 to the 23rd eggs. If I have a mole of tractors, I have 6.022 times 10 to the 23rd tractors. And if I have a mole of ponies, I have 6.022 times 10 to the 23rd ponies. In class, I like to play a game where I take my water bottle, and my water bottle, I usually have the thing, it's probably sitting about half full, and then I have all of my water in there. Well, this, we'll pretend in this case, is 500 milliliters. So, in that 500 milliliters of water, so you drink about 2 liters or so a day, so here I have a quarter of that. I have 500 milliliters. How many water molecules do you think we are drinking? When I play this game in class, students will often guess anywhere from 1,000 up to one of the larger numbers they know. They might guess upwards of 1 trillion. So let's go through and solve for how many water molecules are actually in my water bottle. Now what we can do is if I start with 500 milliliters of water, well, we know that 1 milliliter of water is equal to 1 gram of water. We also know, and again, this is above what you would know at this point, but I just like to do this as a demonstration. I also know that there are 18.02 grams of water per 1 mole of water. And again, I should be going through, canceling my units, milliliters of H2O, milliliters of H2O, grams of H2O, grams of H2O. I'm not writing my H2O right now just because I'm trying to save a little bit of space. And then I know that 1 mole of H2O, remember what did we just talk about? 1 mole is equal to 6.022 times 10 to the 23rd. And that's just a number of something. It could be atoms, could be molecules, could be eggs, tractors, ponies, whatever. In this case, we are talking about molecules of water. And again, here I was talking about water, 1 mole of water. So now I can go through, cancel my units again, cancel those out, and you'll see that we are left in terms of units of molecules of H2O. So now let's go through and actually plug this into our calculator. And when we plug this into our calculator, we get an answer equal to 1.67 times 10 to the 25th molecules of water. To write this in non-exponential form or non-scientific notation form, this is 167 and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 zeros. So go through, add some commas. And you'll see that this is equal to A number I honestly don't know. Very, very large number. Anyway, the reason that I do this is to help students realize just how small atoms and molecules are. And on the next slide, I'm actually going to give you some more examples of just how large this number is. So here are some examples. If we had a mole of watermelon seeds, they would equate to about the size, slightly larger than the moon. If we had a mole of donut holes, they would cover the earth to be 5 miles deep. If we had a mole of dollar bills, stacked one on top of each other the flat way, and this is always the one that most amazes students. Yes, I mean like if these are dollar bills and we're stacking them the flat way on top of each other, they would reach to Pluto and back 5 million times. I don't know, that one always just amazes me, and the reason I think that's fascinating, so to give you an example, a ream of paper is about 1.5 inches thick, and that's 500 sheets. So a mole of dollar bills stacked one on top of each other the flat way, just like a ream of paper would be, would reach Pluto and back 5 million times. So mole is a number so large we can't even start to fathom it. And in the previous slide, we had a number of molecules just in our water bottle was 28 times larger than a mole. So that's just how small atoms and molecules are, and yet we know all this information about them. At the top of the slide here it talks about Skittles activity. That's something that we did in class. So anyway, molar mass is the amount of mass in 1 mole of a substance. So this is the numbers coming from your periodic table. For example, if you look at carbon, carbon says there's 12.011 grams per mole. What that is saying is that if you take 6.02 times 10 to the 23rd atoms of carbon, just say you picked a random scoopful of carbon, well, in there, here's your random scoop of carbon, and you have 6.02 times 10 to the 23rd atoms. Well, some of those are going to be, and this is going back to when we talked about isotopes back in Unit 1, some of those carbons are going to be carbon 12. That means there are 6 protons and 6 neutrons. Some of those are going to be carbon 13, which means there's 6 protons and 7 neutrons. And some, a very small amount, will be carbon 14, which is 6 protons and 8 neutrons. So what happens is if you pick up that scoopful of carbon, or a mole of carbon, that is going to have, in there, you will have about 98.2% of them are going to be carbon 12. 1.07% of them are going to be carbon 13, and about 0.01% of them are going to be carbon 14. So obviously, a scoop of carbon really, since it only weighs 12 grams, that's the size of about half of a Hershey bar, so it's really not that heavy. But in there, we want to know, well, what's the average mass of carbon? Because it's going to be hard to really narrow down to only carbon 12 or only carbon 13 or only carbon 14. So that's why on your periodic table it's 12.011 grams per mole. It is the average mass of a carbon in there. No carbon atom has a mass of 12.01. They can have a mass of 12, 13, or 14, but the average mass is going to be that 12.011 grams that you see on your periodic table, and that is always per 1 mole. So everything coming from your periodic table will always be per 1 mole. And then we have atomic mass, which is the amount of mass in 1 mole of an element. So again, that's the number coming from your periodic table. Formula mass now, the only difference here is the amount of mass in 1 mole of a compound. So atomic mass is an element, which would be one thing coming from your periodic table, say carbon, if you have a single carbon atom. Formula mass would be the mass of a compound, say carbon tetrahydride, or also known as methane. So what you would do when you solve for this is you would take the mass of carbon, of 1 carbon, plus the mass of 4 hydrogens, and we will practice this later, but this would be 12.011, and that's always grams per mole, plus, now you would have 4 times the molar mass of hydrogen, which if you look at your periodic table is 0.0079 or 1.01 grams per mole. And then you would add that together and you would get a total mass equal to 16.05 grams per mole. So that would be, if you had a mole of methane molecules, they would have a mass of 16.05 grams. Alright, so now we're going to learn how to determine the molar mass of a molecule. This might seem very daunting at first, but once you get used to it, it's second nature. But as always, I like to take the slow and kind of ease you into it. So, here, determine the molar mass of sodium. Well, all we do for this is look at your periodic table, and it tells you that it is 22.99 grams per mole. Then you look at the molar mass, and this is saying of O2. Well, on your desk or on your periodic table, it is always 1 mole. That is one single oxygen atom. So when this says of O2, that is an oxygen bonded to an oxygen. So you do need to take that 15.99 of one oxygen. So that 15.99 is per one oxygen, but you do need to multiply that by 2 because we have 2 oxygens bonded together, and you get an answer of 31.98 grams per mole. And now it's having us calculate for a compound of sodium nitrate. So what I like to do, and I just created this table because I know students like to have a set system for how to do this. So you take your element, well in this case we have sodiums, we have nitrogens, and we have oxygens. And then it asks, well, how many do we have? Well, we have 1 sodium, 1 nitrogen. In this case, we have 3 oxygens. Then we fill in the molar mass of each. Sodium is 22.99. Nitrogen is 14, and I'm just going to say 14.01, so I rounded that a little bit. And I'm just going to say 16 grams per oxygen, or you could write 15.99. Then we go through and multiply those all the way across. So this is still just 22.99 grams. Again, it's always grams per mole. And then nitrogen would be 14.01 grams per mole. And then our oxygen would be a total of 48.00 grams per mole. And then what we should do is realistically I could have an equals here, and we go through and we add all of these together, and we get a total combined mass equal to, and this one actually works out really well, we get a total mass of 85.00 grams per mole. And hopefully this makes sense, because if we draw this out, we can have an oxygen. So each oxygen from our periodic table is telling us has a mass of 16 grams per mole. And then we have these sodiums that have a mass of 22.99, and then we can also have nitrogen, which has a mass of 14.01. So I'll just go ahead and color code these really quick. And then if we were to go through and add all this together, so here this nitrogen is 22. This nitrogen, or sodium, sorry, is 22.99. This nitrogen is 14.01, and each one of these oxygens is 16. So now if we were to go through and combine all of them together, which is what a molecule is, we would have these 3 oxygens bonded to a sodium, bonded to a nitrogen, and these would all be forming a molecule of their own. And so this would all be one molecule. So it kind of makes sense that individually they all have their own mass, and then we add all of them together, combine them, and now they have a total mass. It's just all of their masses combined. Again, this might seem incredibly easy because once you get used to it, it is. I just like to break things down a little bit at the beginning to make sure I can explain it as well as possible. Now what I'd like you to do is take a minute and please try this one on your own. Okay, hopefully by this point you have tried this on your own. So what I have done down below here is I have actually taken and drawn what this molecule, just really rough sketch of what this molecule would look like. So keep in mind, when you have this phosphate up here, when you have that phosphate, what that means is that is, as you can see down here, one phosphorus bonded to 4 oxygens. And this 2 subscript down there is saying that we have 2 of that thing, which is why I have the second one drawn over here. This 3 subscript is telling me that we have 1, 2, 3 calciums. So now that we have figured out just how many atoms we have, we take and we write in our elements again. So we have calcium, we have phosphorus, and we have oxygens. And we can go through and count. We have 1, 2, 3 calciums, 3 of the tan dots down there. We have 1, 2 phosphorus, which is 2 of the red dots. And then we actually have 1, 2, 3, 4, 5, 6, 7, 8 of the oxygens, or the green dots. And then we plug in the molar mass of each one of these. And we see that calcium has a molar mass of 40.08 grams. Phosphorus has a molar mass of 30.97 grams. And again, I should be writing this is always per mole. Just trying to save some space. And oxygen, I'm just going to say is 16.00. Again, that's grams per mole. And we go through and multiply these all the way through. And we see that calcium has a molar mass of 120.04 grams per mole. The mass coming from phosphorus is going to be 61.94 grams per mole. And the molar mass coming from our oxygens is going to be 128. Again, I like to keep my hundredths place in there, so 128.00 grams per mole. And then when we go through and add all this together, we get a total mass equal to 310.18 grams per mole. Again, what that's telling me is if I take and I have this molecule, because this entire thing here is what this molecule would look like, is 3 calciums, 2 phosphorus, and 8 oxygens all bonded together. That molecule would have a mass of 310.18 grams for every mole that we have of that. And now is where we begin starting our unit on stoichiometry, which we'll actually begin that more tomorrow, but today is going to introduce it a little bit. So, we would want to solve how many moles. Again, moles are a counting unit. It's how many you have of something, whereas grams are the weight of something. So you can almost think of this like, I can have 30 students in the classroom, but we might have a total weight of, say, 4,000 pounds. So moles are how many of something there are, and grams is the weight of it. So if we wanted to convert for, how many moles are in 30 grams of H2O, we would first want to figure out a conversion. So how many grams are in 1 mole of H2O? Well, again, hydrogen has a mass of 1.01 grams per mole, and we have 2 of those for every water molecule, because, again, water is H2O, and then we have 1 oxygen for every water molecule. So we know that water has a molar mass equal to 18.02 grams per mole. So we're going to take our 30 grams of H2O that it says that we have, and again, we always need to follow our units. So we know if I have grams of H2O on top, I need to get that to cancel out because I want my final units to be moles. So if I have grams of H2O on top, I need to have grams of H2O on bottom, and we know that I have 18.02 grams of H2O for every 1 mole. And so if we go through and solve for this, we can cross out our units. Grams of H2O cancel with grams of H2O. Oh, I'm sorry, I should not have. I did not mean to cross out the number there. Only the units cancel out. The 18.02 stays, so then we take 30 divided by 18.02, and you will get an answer equal to 1.67 moles of H2O. And realistically, I should have followed sig figs, so I'm going to say that this is 30.0, I'm going to say that this is 30.0, and that way I can follow my rule of 3 sig figs. And that kind of makes sense. We figured out that 1 mole was equal to 18.02 grams. So if I have 30 grams of it, I should have, probably about 1.6 moles of H2O. Now for a little extra fun, how many molecules of water would this be? Well, now we're going to start, and we know that 1 mole of water is we know that we have 1.67 moles of H2O. And we know that for every 1 mole of H2O, we would have 6.022 times 10 to the 23rd molecules of H2O. And so when we go through and solve this, we get an answer equal to 1.00 times 10 to the 24th. And again, that is molecules of H2O. So these are all kind of saying the same thing. 30 grams of water. So the 30 grams of water that we had up top here is equal to 1.67 moles of water, which is equal to 1 times 10 to the 24th molecules of water. They're all saying the same thing, they're just talking about something a little different. So one is talking about the weight, one is talking about a counting number, and now we're talking about the molecules. And for these last couple problems, if you want to go through and do those, you may, but I'm not going to cover those in this video lesson. Alright, so now we want to solve for how many grams are in 0.750 moles of CuCl2. So again, we need to reference like we did back to that slide where I showed you how to find molar mass of a molecule. So here we have copper and we have chlorine. We have 1 copper, we have 2 chlorines. Copper has a molar mass of 63.55 grams per mole. Chlorine has a molar mass of 35.45 grams per mole. And so we find out our total molar mass coming from copper is 63.55. Our chlorine needs to be doubled, so we have a total molar mass of 70.90. Now we add those together and we find out that our molar mass of copper chloride is 134.45, and that is grams per mole. So what this is telling us is our starting information here. What we're starting with is 0.750 moles of copper chloride. So we're going to put that in the top left. And now, since I have moles of copper chloride on top, I need to put moles of copper chloride on bottom. Well, we figured out that this 134.45 grams is per 1 mole, because anytime you're adding up stuff from the periodic table is always per 1 mole. So now if we go through and do this, we see that we have 1 mole per 134.45 grams of copper chloride, which would mean that it is equal to 101 grams. And again, that should kind of make sense when you reason it out, because 1 mole was 134.45 grams. So if we have 3/4 of a mole, it should be equal to about 3/4 of the weight. Again, I would like you to please take a minute, pause the video, and try and solve for this one on your own. Okay, by now hopefully you have tried this problem. So in here we need to figure out the molar mass of calcium nitrate again. So we have calciums, we have nitrogens, and we have oxygens. Well, we have one calcium. Again, this subscript is going to multiply through, so that would mean that we have 2 nitrogens, and it's multiplying, so we would have 6 oxygens. Calcium has a molar mass of 40.08 grams per mole. Nitrogen has a molar mass of 14.01 grams per mole. And oxygen has a molar mass of 16.00 grams per mole. And so if we go through, total all of this up, we're going to multiply again. Calcium is going to add to the overall weight 40.08 grams. Nitrogen is going to add 28.01 grams. And oxygen is going to provide 96.00 grams. And when we add all of that together, we're going to have 40.08 plus 28.01 plus 96. And calcium nitrate has a molar mass of 164.09 grams per mole. And so this is telling us that we're starting with 270 grams of calcium nitrate. Well, we know that every mole of calcium nitrate is equal to 164.09 grams. So we know that our answer should be probably somewhere close to 2 moles. Because if you double the mass of this, you get an answer of about 320. So we should be saying between 1 and 2 moles. So if we start this problem off, we have 270 grams, and that is not of copper chloride. That is grams of our calcium nitrate. And then we have 164.09 or 164.10 grams of calcium nitrate per 1 mole, which we found up top here. So when we go through and solve for this one, we will see that we get an answer of 1.6. And again, this should not say grams. I apologize for the typos. This is 1.6 moles of calcium nitrate. Because we cancel out our units, grams of calcium nitrate cancel out, grams of calcium nitrate cancel out, and we are left with moles of calcium nitrate.